Hi everyone, my name is Tom Compagno, and welcome to my course Connecting and Deploying Amazon ElastiCache. I'm the VP of Technology at Contravent. Speed is everything in today's technology, be it your website, your data warehouse, or even your client chat communications. Everything is better when it's faster. In this course, we're going to demonstrate how easy it is to stand up a cache that can be used to support just about any application deployed in your AWS ecosystem. Some of the major topics that we will cover include standing up a Redis cluster in breakneck time, configure an AWS VPC to support multiple connection points to your cache, look at ways to scale and keep your cache resistant to failures, build out a Memcache cluster, opening your caching options to even more use cases. By the end of this course, you'll know how to launch a scalable and resilient cache to support all your system needs. Before beginning the course, you should be familiar with some AWS networking concepts, as well as an understanding of what caching technologies like Redis and Memcache are commonly used for in a system architecture. I hope you'll join me on this journey to learn ElastiCache with the Connecting and Deploying Amazon ElastiCache course at Pluralsight. Welcome to this course, Connecting and Deploying Amazon ElastiCache. My name is Tom Compagno, and I'm happy to introduce this extremely versatile service from AWS. For many of you as database administrators, you may have already set up caching capabilities for your software, leveraging tools such as Redis and Memcache as standalone implementations. In this course, we're going to show how easy it is to create these same capabilities using the AWS ElastiCache service and stand up multiple variations of Redis as well as a variation of Memcache, which can scale as needed and provide multiple levels of fault tolerance. Maybe you're only familiar with one of the technologies. There are a number of similarities between Redis and Memcache. The first is that they are both in-memory data stores, meaning they hold data in memory first, making them both extremely highly performant. Often these technologies are used to enhance database or API access, pulling data closer to the user and serving it from memory instead of from a drive persisted store. Second, they're both designed to be easy to use once set up. They are meant to do one thing very well, which is to store and return cache data as quickly as possible. And because they often serve as a critical component of highly scalable and performant architectures, they are also designed to spread their data across multiple nodes, providing greater scale to meet a growing application's needs. Now that we understand some of the benefits of Redis and Memcache, why use AWS ElastiCache? Well, as a standalone cloud service, ElastiCache offers a number of benefits over using these platforms in a standalone implementation. First, you no longer need to perform operational tasks such as hardware provisioning, software patching, complex setup, configuration, or even failover recovery. This allows you to focus on executing the final delivery of the services that your team needs. Second, by using an AWS service, you have access to additional capabilities such as monitoring metrics without any additional software to install, and this enables you to get up and running with less dependencies and allows you to diagnose and react to issues leveraging proven toolsets. Finally, by running as a service instead of an installed application, you can take advantage of cost-efficient and resizable hardware capacity, scale up and down as demand changes, and keep costs in control as your needs change. To demonstrate as much of the capabilities as ElastiCache has to offer, this course is broken into 4 key modules, each focusing on the key features of ElastiCache. Because of the complexities of Redis, the first 3 modules stay focused on Redis. The first will show how to build a simple cluster with ElastiCache. We will walk through cluster requirements and also work through how to properly connect to a cluster from within AWS, as well as creating a path to connect to the cluster from outside of AWS. After learning the basics, we will then walk through a much more robust Redis cluster. This will show more of the full capabilities available from ElastiCache and touch on why those expanded features are important. The final Redis module is about scale and failover. Caching services are often a critical component for an application. You will want to know how to properly scale clusters in different ways, learn about restrictions, as well as how to back up the clusters in preparation for restores or any worst-case scenarios. The fourth module will be focused on memcached. Because memcached is slightly more basic, we will dedicate this module to building a cluster, show how to connect to it, as well as properly scale it for future growth. Last but not least, we'll review what we learned and discuss differences between the technologies and other possible use cases to help provide the best recommendation to your team or help you decide which platform is best for your specific need. Let's dive into the first topic, which is how to build a simple Redis cluster. We can start by reviewing what we'll accomplish in this first module. First, we will take a look at what a real-life use case could be, which will help guide us on our implementation. Based on that use case, we'll take a look at a high level what kind of Redis system we hope to create. Next, we'll want to review some of the prerequisites you need, not only for this course, but also what pieces of information are often relevant before starting an ElastiCache build. Then we'll jump into AWS and start building our simple cluster, step by step until our system is ready for data. Before we can test our new cluster, we'll need to walk through the various ways to set up access control in AWS, so be prepared to touch on some AWS security topics as well. Finally, once our access is set up, we can do a couple of quick tests to verify our cluster is actively storing our data. Your company, Globalmantics, has a development team in need of a Redis cluster for their new application design. That team has given some basic requirements. First, it needs to be on the latest version of Redis, at least the latest version AWS supports. The team has a backup file of seed data. They will use this for testing, and they would like the new cluster to be seeded with this data file. Because this is a new application, they only need a basic cluster set for development and testing purposes, so it doesn't need to scale or be failover capable. Just a basic implementation will do fine. The final requirement is that as developers, they want to be able to test from their local machines, from within the Globalmantics network. That means they need the cluster to be accessible from outside of AWS. A simple Redis cluster can be visualized in this way. The outside box represents the cluster itself. Within a cluster mode disabled cluster, there will exist one shard. A shard, also known as a node group, is simply a representation of how all of the data is spread within a single cluster. In this case, for a simple cluster, it is a 1-to-1 ratio. Every shard will have a primary node and 0 to 5 replica nodes. Those replica nodes have an option of being spread across one or more availability zones in AWS. By spreading your replicas across availability zones, you get two key benefits. The first is higher availability when accessing your cluster from different locations. And second, when your primary nodes fail over to your replicas, your cluster is protected from your primary node's failover caused by problems within its current zone. AWS provides multiple engine versions to choose from, which provides a DBA more flexibility by allowing clusters to be created in AWS, which can be aligned to older versions of clusters deployed within an organization. In our example, we'll be using the most recent version, 5.0.3, which is available at the time of this recording. Sizing your node's memory requirements is important when planning your cluster. You can get a general estimate by taking the size of the items you want to cache and multiplying it by the number of items you want to keep in the cache at the same time. Older versions of Redis required more memory, so if you need to run older engine versions, make sure you take that into account in your overall calculations. If you have a heavy write application or need to do failovers within a simple cluster, you may need to double the size of your node to handle all the storage. In our case, our Globomantics developers only need a simple cache with the smallest possible node type so they can do their development work. Lastly, since our developers need access to this cluster from an AWS EC2 dev server, as well as outside of AWS, we will need to set up some network and security components ahead of building our cluster to allow this communication. Let's switch gears now and talk a little bit about AWS security. Let's look at the different ways we're going to access our cluster. Our developers need to access this cache from both an EC2 development server inside of AWS, as well as a developer's local PC outside of AWS. This means we need to set up security in a way that allows someone from the outside to connect into our AWS network, as well as create an EC2 instance for our developers to run their development server on. While our use case calls for clusters to be accessible from outside AWS, it's not typically recommended to run a cluster in production that is accessible from the internet. Our AWS only access network diagram will look something like this. This part of the course assumes you have some basic understanding of AWS networking and security. It is beyond the scope to go into too many details, but I'll try and keep it straightforward while building these parts inside of AWS. We start with a single VPC or virtual private cloud. Think of it as our contained network infrastructure. Surrounding both our cluster here and our EC2 dev server here are two different subnets, one private and one made public by connecting it to an internet gateway. The cluster and the EC2 dev server are attached to two different security groups. What we want to do is allow the two security groups to talk to each other over the Redis standard port, which is 6379. We can do that by creating a TCP rule connecting the two security groups. More on that process later. Let's look at how we can open this cluster to someone outside of AWS. In order for the outside world to access our private cluster, we will need to add an intermediary acting to forward all the traffic between our public and private subnets. We do this by adding a NAT, or Network Address Translation, EC2 instance. This will get its own public IP address, and any request for our Redis port will be forwarded to our Redis cluster for processing. This obviously adds overhead and is one of the reasons AWS does not suggest using this for a production cluster. It's only to allow cluster testing from a public source. This also opens a security hole, so it should not be used in production or any other secure data. This course covers a lot of material in a short time period. We will jump between the AWS console as well as a command or terminal window, so let's get building our caches. Welcome to our first demo. In this demo, we will start by working in the AWS console. This course assumes you have some previous experience working in the console. We will pre-build some networking and security components to leverage during our cluster build. After which, on the next step, we'll go over the major components of building a Redis cluster. These include standard settings, advanced settings, security, seeding our cluster with some data, as well as some final configuration pieces. After our cluster is built, we'll finish the networking setup, and finally we'll verify we can access our new cluster from multiple sources. Let's dive into the first topic, which is how to build out a simple Redis cluster. Starting from your AWS Management Console, let's search for the VPC service by entering VPC into the search field here. This is going to show us the result we want, which is VPC. This will take you to our VPC landing page. What we want to see is our list of VPCs. We can access those by selecting the items on the left. Obviously, while we run through any demonstration within AWS, your list of services may be different from mine, either because you already have built services within your own AWS account, or I have within mine. I will keep you focused on only the information required for our education. I have my default VPC here, but I want to create a new VPC, so I click on Create VPC here. That will take me to this page, which is a simple new VPC form. Let's walk through the values we're going to use. First, I want to give our new VPC a name. I choose something explanatory for what I want to use it for, which is simple Redis VPC. Next, we want to give this VPC a CIDR block. We will keep it simple and give it 10.0.0.0/16, which will give us plenty of addresses for our needs. I don't need the IPv6 features for our demo, so I'll leave it off and choose the default tenancy. Now click Create here. You should see a success page similar to this. Click Close. Back to our list of VPCs, we should see a new VPC now in the list. Next, we need to add some subnets to our VPC. Remember, we want one of them to be private and one to be public. Let's click the subnet link on the left menu here. Again, you may already have subnets from other VPCs. Let's create our first subnet by clicking Create Subnet here. Let's start by building our public subnet. We'll name it something that helps us remember the subnet details. For this example, we will name it with the CIDR block range and availability zone that we will see below. Don't forget to choose our new VPC we just created. It should be in the drop-down list. Choose the correct availability zone to match your name and enter the CIDR block of 10.0.1.0 and /24. Remember, the 1 block is our subnet block. We will also be creating a 2 block, which we'll use for the private subnet. That's where our cluster will live. Click Create to move on. If successful, you should see a screen like this. Go ahead and click Close. Our new subnet is now visible in our subnet list. Again, let's create our private subnet by following the same steps. Go ahead and click Create Subnet here. This time we'll name it slightly different. We'll use the 2 instead of a 1, and we'll use the US East 1B availability zone. Don't forget again to choose our new VPC and match the CIDR block. This 2 range will be our private subnet moving forward. Private means it will not have direct access to the internet. Our success screen again. Click Close. I can see both of our subnets in the subnet list. The next step in the process is to create some security groups. This will help us connect and open ports to allow access to our various systems. Click on Security Groups in the left menu here. This is a similar process. To create a new group, simply click Create Security Group here. Only 3 basic fields are required to create our group. Let's first create the group that will be attached to our future simple Redis cluster. We can call our group the same to help keep it clear. I will give a short description to explain the security group will be used to open the Redis ports. And again, I must choose our VPC cluster here. Click Create to move on. My group was successful. Let's find it in the list. Click Close. I can see my new security group. Let's click on it and add some more details. I need to add a new inbound rule. This rule is required to give access to our Redis cluster. Click here on Edit Rules to add another. Click Add Rule. Fill in these details. We want this to be a custom TCP rule with the default Redis port of 6379. And we want anyone to have access to this port if they have access to the security group. So simply enter 000/0. And finally, apply a description to help people understand the rule's use. Click Save Rules to move on. Our rule is saved. Click Close. We have one more security group to add, so again, click Create Security Group here. We need a security group for our development EC2 instance. This will be living in our public subnet. Let's look at those details. I want to call it something specific like Dev Server Security Group. This group will need to allow me to connect to the dev server via SSH, and eventually we will use this security group to do some port forwarding. So I want to reference that in the description as well. And finally, reference to our new VPC here. All of these parts are starting to come together. Click Create. You should see success again. Click Close to head back to our list. Click on our new group and choose Inbound Rules again. We need to add our SSH rule first. Click Edit Rules. Click Add Rule and provide these details. If you choose SSH from the first dropdown, some details are added for you. Port 22 is the standard for SSH. and I'm going to open it to anyone using the 0000/0 again. Then a quick description to show why we need SSH, and now I can save the rules. Again, success. Click Close. That's all we need to do for now with security groups. From here, we have enough of the pre-security set up that we can go build our simple Redis cluster. We will continue the next part of our demo in the next video. Welcome back. Let's get started building our cluster. If you aren't back in the AWS console, head there now. From the services menu here, let's jump to where we need to go. Type ElastiCache in the search and choose the first option from the dropdown. You should end up on a default landing page like this. Our first cluster is going to be a Redis cluster, so choose Redis from the left menu here. Next, to get started, click Create here. This is our template for creating a Redis cluster. We will move through each field and talk about what it means and why we are choosing the option we chose. First, we have Redis selected, and we're building a very simple cluster, so we don't need to enable cluster mode. We will touch on cluster mode in a later module and discuss its advanced capabilities then. I give my cluster a name. For our purposes, I choose Simple Redis Cluster. Next, you can choose an engine version. Our use case calls for the latest version, which is 5.03 at the time of this recording. But your use case may call for a different version. This is where you can choose. I'm going to leave our default Redis port of 6379, as well as the default parameter group entry. You may have multiple clusters in your environment that all have the same Redis parameters. Instead of setting those parameters during every cluster creation, you can simply build a group and select that group here. The next field is one of the most important settings of a cluster, and that's the node type. Because ElastiCache is in-memory data storage, you need to choose a node type that has enough memory storage capability to cover your entire caching needs. As a DBA, you may already have this data calculated, but at a high level, it's usually the size of the data item you will cache multiplied by how many you will actually cache. Other things to consider are older versions of Redis require more memory, heavy write caches require more memory. For example, taking a snapshot may require double the size of your actual cache. Also, for complex clusters, your node type should represent a division based on the number of shards in the cluster. For example, if you need 10 gig total, you would want a node type of 5 gig each if you have 2 shards. When selecting your node type, this pop-up will help you understand all the variations of sizes available to your cluster. For our simple cluster, we will go with the Cache T2 micro version. For each primary node, you can have 0 to 5 read replicas. For our use case, we don't need any replicas, so let's select 0. There are some advanced settings we need to add to ensure our cluster is set into our network, as we need it to fit the use case requirements. We have already configured the appropriate network components, so let's check what the value should look like. Based on our network diagram, we want our cluster to live in our private subnet that we previously created. To add our cluster to that subnet, we start by creating a new subnet group for this cluster and name it Simple Redis Subnet Group. Of course, select our new VPC we created previously, and you can see our 2 subnets available. We want to place this cluster inside our private subnet, which is the 10.0.2.0 option as seen here. We can leave no preference on which availability zone to use, but we do want to select our previously created Simple Redis Security Group. The last few items we need to also adjust based on the requirements. This seed data field is an optional step for you. I am adding the seed data file for demonstration, and also so we can reference that we are correctly accessing the cluster by reading specific keys and validating the results from data within that seed file. If you want to use the seed data file, you will need to upload it to an accessible S3 bucket in AWS and reference it like my example. I have added my seed file reference. I am going to disable backups because I can recreate this cluster at any time using that seed file, and the use case does not require backups for failover. I also don't have a preference for when AWS may do their maintenance on my cluster. That is all I need to get my simple cluster running. Go ahead and click Create here. While we are waiting for our cluster to start up, let's jump back to the VPC area from the Services menu to add some additional networking components. Selecting VPC from the search items. Part of our network requires what is called an internet gateway. Essentially, it connects our VPC to the internet, allowing access to and from outside resources. Let's quickly create one by jumping to the gateway list from the left menu here. My default VPC already has an internet gateway, but let's create a new gateway for our new VPC by clicking Create Internet Gateway here. All it needs is a name. Let's make it simple and call it IG Simple Redis Cluster. IG for Internet Gateway. Click Create here. You should see success. Go ahead and close this page. By default, a gateway is not attached to any VPC. So let's attach this one to our new VPC. Select our new gateway that clearly shows as detached here. Then from the action menu here, choose Attach to VPC. You should be able to click into the VPC input here. Find our new VPC from the drop-down and select it. Then click Attach to attach our new internet gateway to our new VPC. Our gateway shows in the list as attached. From here, we need to add a couple of routes within our network to ensure all the various components can pass traffic around as we need it. Click on the route table link from the left menu here. Let's add a new route table by clicking Create Route Table here. Our new table only needs a name and a VPC for reference. Let's call this one our public route and select our new VPC. Then click Create. Success. Go ahead and close this. Select our new public route from the list and click on the Routes tab here. Then click Edit Routes. We want to add a route that allows all traffic to head to our new internet gateway. So add 0000/0 as the destination and start typing IG in the target field to find our new internet gateway. Then click Save Routes. You should see a successful result. Close this. Back in the routes list, if you select our new route table, you should also see our new route in our table down here. The last thing we need to do is associate this route with a subnet. So click the Subnet Associations tab here. Then click Edit Subnet Associations here. And find our public 10.0.1.0 subnet and make sure it's selected. Then click Save. Our traffic should be routing as needed now. Next, we should add our dev server to the network and verify we have access from that dev server to our Redis cluster. Let's do that in our next video. Let's use this time to set up a dev server in our network and verify it has access to our new cluster. If you aren't in the AWS console, head there now. Let's use the Services menu to jump back over to our EC2 list. Search for EC2 and select it from the list. Let's look at our empty list of running instances by clicking this link. I have a couple of recently terminated instances in my list. You can ignore those as we want to create a new development server for our dev team's use case. Let's create that by clicking Launch Instance here. We just want a basic Linux server to run our tests. So select the first Amazon Linux image by leaving the default and clicking here. Again, we will leave the default at T2 Micro for our needs and click Next here. From this screen, we need to make a couple of adjustments to the defaults. We first want to put this in our new VPC. We updated that in this networking field. Then we want our dev server to live in our public subnet, not the private subnet where our cluster lives. So we chose 10.0.1.0 for the subnet. Finally, we want to choose to enable auto assignment of an IP address so we don't have to try and do this again later. This will let AWS give our server a public IP address. The rest can be left at defaults, and let's click Next. The default storage looks fine. Click Next to add a name. Click Add Tag and put name in the key field, and Dev Simple Redis Server in the value field. The rest can leave at the defaults for now. Click Next again. From here, we want to choose one of our previously created security groups. So choose the Select an Existing Security Group option here. And now select the security group we call Dev Server Security Group from the list. It should show our SSH rule down below. Now we can do one last review of the settings and launch our server. You will probably see a warning about our server being open to the world. That's okay for this example, but normally you'd want to restrict access to new servers, maybe to a specific IP address as an example. Go ahead and click Launch to get our server running. One last step, since we will be accessing the server via SSH, you either need to choose an existing key pair from your AWS security setup or create a new one. This step will either require you to have the PEM key file downloaded from an existing pair, or make sure to download the new one and keep it somewhere safe so we can reference it in a later step. Click Launch Instances. We are successfully launching our server now. You can check the status by clicking View Instances. While that is loading, let's go to our Redis cluster and get the endpoint so we can test it from our new dev server. Use the Services menu to jump over to ElastiCache Service and find your Redis cluster list. From our cluster list, we can click on this arrow to show the cluster details. We are looking for the primary endpoint here, but without a port number. Go ahead and copy that information somewhere handy, and we'll use it for later testing. Next step we need to take is to test we are able to access our cluster from our new EC2 dev server. Let's jump back and get our server IP address. To do that, use the Services menu as usual and search for EC2 to head back to our EC2 dashboard. Click on Running Instances again up here. In order to connect to our dev server, we're going to need its public IP address. My server's IP address is located here. Copy this information and keep it somewhere handy for the next step. In order to connect to the server, you will need SSH. This requires an SSH tool. If you are on a Mac, you have one by default. If you're on Windows, you're probably going to need to install some extra software like PuTTY. I will not be demonstrating how to make an SSH connection via Windows, but we'll step you through doing it on a Mac in a terminal window. If you are a Mac user, go ahead and open a terminal window to follow along with the next part of the demo. Okay, I'm currently located in the Downloads folder where I stored my key pair PEM file during the last step of the EC2 creation process. In order to connect via SSH, you need to enter this command, SSH, then the username for the server, which is EC2-user for an AWS Linux server, then the @ symbol, and the IP address of our server. You will need to replace this value with the value you just copied from your dev EC2 instance in the previous step. Next, leave a space and add a -i, another space, then the PEM file from your key pair. Again, this is my file name. You need to replace it with your file name or the full path to where your file is located on your machine. Then click Enter. If everything's working, you should see this warning. Go ahead and type yes and click Enter. You should see something similar, showing that you are now remotely connected to your dev server in AWS. In order to connect to the Redis cluster, we need to install a bit of software quickly. To start, type in this command, sudo yum install gcc, which will install a compiler to your new instance. You may see a question like this. Go ahead and click Y and enter to continue installing. It will do some churning and if successful, tell you it's complete. Next, we need to download the Redis client. Do that by entering the command wget and then this path, and click Enter. This will download a source package. Next, we need to get the contents of this file to compile and run. To export the content, use the command tar xvzf and then the path of the file, and hit Enter. It should run through a big list of files that it just wrote into a directory called Redis stable. Change directory cd redis-stable. Once there, type the command make dist clean and hit Enter. Now enter the command make, which will compile our new software so we can run it. Make and enter. This might take a couple of minutes to complete, but if successful, you should see something similar to this result. Before we continue, we need to get a piece of data for another future test. Type the command ping and add the primary endpoint value you copied from your previous step related to our Redis cluster details. It should look similar to this. You can hit Control-C to cancel the request. All we need is that IP address, which you'll want to store somewhere safe for later. My example is 10.0.2.227. Now we are ready to test if we can access our cluster from our dev server. To do this, first we connect to the cluster with this command. Your command line value should change to show your endpoint and the 6379 port. This indicates you are now connected to your cluster. Because I seeded my cluster, I know I should have a key named A with the value of key A. So to test I'm looking at my new cluster, I'm going to look up that cached item. I enter the command getA, and my result is key A, as I expected. This means I have successfully connected to my node. That is only part one of our cluster access tests. We have tested connecting from our dev server to our Redis cluster. Now we need to access the Redis cluster from outside of AWS. To do that, we need to add another server into the public subnet so we can forward requests from the internet into our cluster and back out. Let's follow that process in the next video. The last part of our first use case is to be able to access our cluster from outside of the AWS network. To do this, we need to create what is called a NAT, or a Network Address Translation Instance. It is essentially an EC2 server that's pre-set up to proxy traffic around AWS. So let's jump back into our EC2 list in the AWS console. Repeat what you learned in the previous video by going back to your list of EC2 instances, and like before with your dev server, click on Launch Instance. From the Launch Instance screen, instead of choosing the first option like before, click over on the Community AMIs tab so we can search for a NAT image to use. Search for NAT, and the first result should be fine to use. Go ahead and click Select. Default of a T2 micro will work fine for our needs. Click Next. As with our dev server, we need to choose our new VPC, add it into our public 10.0.1.0 subnet, and enable auto-signing of IP addresses. The rest we can leave at default and move to the next step for adding storage, here. Leave the defaults, and let's add a name to our new NAT instance. Add a tag called name, and set its value to be NAT Simple Redis Server, and leave the rest at defaults. Then click Next to configure the security group. This instance should also go into our dev server security group. But we will need to add a couple more rules, which we will do in a future step. Go ahead and click Review and Launch. You may get a screen like this. Go ahead and choose the default. This NAT machine image may be out of date, as SSD is the new standard for storage rather than magnetic. Click Next to accept the change and continue. Same warning as our dev server because we chose the same security group. In our case, we can ignore it. Click Launch to get our server running. Don't forget to keep or create a new key pair somewhere so we can SSH to our server again in the future. If you lose the key, just delete the server and rebuild it again. Click Launch. Click View Instances to see both our new servers. I mentioned we will need to add a few new rules to our security group for our NAT server. So let's do that now while the server is still starting up. Jump to VPC from the Services menu and click Security Groups in the left menu from the VPC dashboard. We need to add more rules to our Dev Security group. Select our Dev Security group and click in the Inbound Rules tab, and then Edit Rules to add new rules. From here, we want to add a rule that allows the Redis port from all incoming traffic, as well as a Redis port from our cluster security group. In a more secure setup, instead of allowing all traffic, you may only include a specific IP address or a range from your company. It is always best to use as specific as possible from a security standpoint. But for our demo, I'm opening it to everyone, so you can access it during the demo from wherever you're located. Save these updates. Last change is to the outbound rules. Click on that tab here and edit these rules by clicking here. Let's also add the Redis port to our cluster security group as a rule, so all our traffic can be forwarded back and forth appropriately. Save these rules, then jump back to our EC2 instance via the Services menu. First step is to grab our public IP and keep it for a near future step. Go ahead and grab it from here. By default, an EC2 does not allow traffic from outside itself to be forwarded. But since that's exactly what we need our NAT server to do, we need to disable this feature. To do that, select our NAT instance from the Actions menu here, click Networking, and click Change Source Destination Check here. You will get a verification pop-up. Go ahead and click Yes, Disable. Next step, we need to head back to my Mac's terminal window. Head to your Mac terminal window now. Using our IP address to our NAT server we just grabbed in the recent step, let's SSH into that server using our PEM key file. This should feel very similar as before because we connected the same PEM file as our dev server to the new NAT machine. The only change to make is the IP address. Again, type yes to continue and hit enter. We are now connected to our NAT server. Since we're going to be making some low-level network changes in this next step, be sure to elevate your user to root by typing the command sudo su before doing anything else. Next, we want to add a record into the IP tables of our NAT server. Here, we're essentially telling our server to send all traffic it sees that's coming through on port 6379 over to our cluster node endpoint IP address. This IP address we grabbed from an earlier step. Go ahead and click enter. You shouldn't see any messages if it was successful. Now let's save that change by entering the command service IP tables save and hit enter. It should give you a message like this, telling you the firewall rules have been changed. Next, I'm going to start a new Mac terminal window and attempt to connect from my local Mac through my NAT server and into my Redis cluster. From this new window, I've previously installed a Redis client for my Mac. There are a large number of clients available in a wide range of languages, so I won't step you through installing one. Find one that fits your specific use case. My Redis client has a simple command line like this, rdcli-h, and the IP address of my NAT server, which we grabbed earlier. Clicking enter, you see my command prompt changes similar to when we ran our client through the dev server. This indicates I am now connected to my cluster via the NAT server. Let's run our test again. I enter get A, and I correctly received key A as a result. Success. I was able to access the simple cluster from a local machine, satisfying the major components of our first Global Mantics use case. Let's double check we did hit all the requirements. We created a cluster using the latest Redis version. We seeded our data file. We didn't set up any bells and whistles because they didn't need failover. And finally, we connected from a dev server inside of AWS, as well as from a local machine outside of AWS. In the next module, we will set up a more complex Redis cluster and explore some of the more advanced features available via ElastiCache. Welcome to this module of connecting and deploying Amazon ElastiCache. My name is Tom Compagno, and I'm excited to show you some of the more advanced features of ElastiCache. In the last module, we built and connected to a simple Redis cluster. In this module, we're going to explore some of the advanced features to show off the scalability and resilience ElastiCache can provide for your application. Let's start by taking a look at what we'll cover in this module. Like before, we want to apply what we learned to a real-life use case. So we'll start by reviewing what the Global Mantics guys want. Then we'll take a look at the basic architecture of this slightly more complex cluster setup. We will then dive into another round of AWS network setup. This version will be similar, but with a few extra bells and whistles to help show off some of what the new advanced cluster can do. Once the network is ready, we will go through and build our cluster. Again, it will feel similar to the simple cluster, but we're going to show off those extra features it can do. After our cluster is ready, we will set up a few more security components, and finally, verify we can access our cluster. Your company, Global Mantics, has a development team in need of a production-ready Redis cluster for their new application. That team has given you some specific requirements. First, it needs to be the latest version of Redis, at least the latest version AWS supports. They need replication enabled. Specifically, they want 2 read replicas for each primary node. They also want each replica to live in a different availability zone. Because of the volume of data and traffic they expect to see, they want to partition the data, meaning they want it split across 2 matching shards. The final requirement is that they can access the cluster from their new production server, which is an EC2 instance in AWS. If you already followed along in the previous module, this diagram should look familiar. It is our previous simple cluster architecture. We have a single shard with a primary node, and we did not enable any replica nodes. It was a basic use case. Let's see what we're about to construct in this module. This is our new complex cluster. Again, the outside box here represents the cluster itself. Within our cluster mode enabled cluster, there will exist 2 shards. A shard, which is also known as a node group, is simply a representation of how all the data is partitioned within a single cluster. In this case, for our complex cluster, we are choosing to spread our data across 2 shards. For simplicity, we could say keys starting with A through M go to shard 1, and keys N through Z go to shard 2. You can create a cluster with higher number of shards and lower number of replicas, totaling up to 90 nodes per cluster. This cluster configuration can range from 90 shards and 0 replicas to 15 shards and 5 replicas. 5 replicas is the maximum number of replicas that are allowed in any one group. Each of our shards will also have replication enabled via 2 replica nodes. These can live in multiple availability zones. So in our demo, we'll show how to put some nodes in separate availability zones. Using multiple availability zones can help ensure your cluster has better fault tolerance, as well as fastest access depending on where your cache is being accessed from. We will set up our network configuration almost identical to our previous module. Again, I will step you through this setup, but it will go smoother if you have some previous experience with AWS networking. We start with a single VPC or virtual private cloud. Think of it as our contained network infrastructure. Surrounding both our cluster here and our EC2 production server here, there are 3 different subnets, 2 private and 1 made public by connecting it to an internet gateway. Our second private subnet is going to live in a separate availability zone, so our cluster can see it. The cluster and the EC2 dev server are attached to 2 different security groups. What we want to do is allow the 2 security groups to talk to each other over the Redis standard port, which is 6379. We can do that by creating a TCP rule connecting the 2 security groups together. Let's again jump into the demo and get building. Our demo has 4 main parts. As always, we'll start in the AWS console, so jump there when you can. The first part, we will pre-set up the new VPC we just reviewed. Next, we will build out our new complex cluster. You can also review the previous diagram for reference. We will do some final network setup. And finally, we will show what it's like to access this more complex cluster from our new production server. Let's dive into the first part of the demo. Head over to AWS if you aren't already there. Starting at the console or using the services menu, let's do a quick search for VPC. AWS should find it and show it in the dropdown like this. Go ahead and click there. This is the VPC dashboard. Let's look at our VPCs by clicking here. You probably have a list of VPCs, or at least like me, the default VPC. We want to construct a new one, so click Create VPC here. We are presented a simple form. Let's fill it out. I'm given an explanatory name called Complex Redis VPC. Seems appropriate. Then in our network CIDR block, we're going to put 10.0.0.0/16. This will be our network range. And we'll leave the other values at default. Now I click Create. Success. Go ahead and close. You should land back to our VPC list, and you can see our new VPC here. Next, we need to create some subnets. Let's go to that area by clicking subnets over here. From our subnet list, we can jump right in and click create subnet. Our first subnet, we want these values. We will name it with 10.0.1 and East 1A to help reference our CIDR range and our availability zone we chose over here. Don't forget to choose our new VPC from the list. Double check the values and then click create. 1 down, 2 to go. Click close. Same process to create another. This time we do 10.0.2 and same zone. And always check to make sure you select our new VPC. And click create. Click close and create another one. Last one. This one will be 10.0.3 and we'll use a different zone this time. Use US East 1B and of course our new VPC. Click create. Okay, done with subnets. Click close and then click into security groups from the subnet list using the menu on the left. If you found security groups okay, it should look like this. Again, if you watched the previous module, this will feel familiar. Click into create security groups here. Our first security group will be for our cluster to live in. So call it Complex Redis Cluster Est Group. I gave it a description for why we need it, and that is to allow access through the Redis port. And don't forget, use our new VPC. Click create. 1 down, 1 to go. Click close. Our second group is where the production server will live. So call it Complex Redis Prod Server. And it will allow us to SSH into our server from the internet. And don't forget, select the new VPC here. Click create. Security groups are built. Let's add an internet gateway next. From our security group list, click Internet Gateways here. Click on Create Internet Gateway up here. All we need to do is give it a name, which we add as IG Complex Redis. And then we can click Create. Okay, a little more config to do on our gateway. Click Close. Back in our list of gateways, click on the checkbox of the one we just created. It should say Detached in the list. With our new Internet Gateway selected, click the Actions menu and click Attach to VPC here. Select our new VPC from the list and then click Attach over here. It should now be attached to our VPC. Okay, next step is to help our gateway talk to the rest of the VPC. Let's set up a route table for it by clicking Route Tables over here. Let's create a new table by clicking Route Table here. Fill in the form with the name Public Route, and please select our new VPC. Did I mention to select our new VPC? Click Create. Almost there, hang on, click Close. Okay, select our new public route and click Edit Routes down below. Add a route with the Add Route button and fill in the destination as 0000/0 and in the drop-down choose Internet Gateway and find our new gateway we just created. Once you have those values in place, click Save Routes here. Your route details should look something like this. One last step is to associate this route with our subnet 10.0.1 to make it our public subnet. So click this Subnet Associations tab, then click Edit Subnet Associations here. Find our 10.0.1 subnet and select it and it only, then click Save. Now all the big parts are set up for the next stage where we're going to build our cluster. Thanks for hanging in there. It was many small steps, but congrats on finishing this part of the demo. In the next video, we'll do the work of actually building our complex Redis cluster. See you then. Welcome to the next section of our demo. In this part, we're going to build our complex cluster. It should feel similar to our simple cluster setup if you went through that video, but we will definitely have a few more settings to add. So let's jump in. Head over to your AWS console. We need to be in ElastiCache. So search for ElastiCache in the Find Services field or use the Services menu and click the correct item. From the dashboard, we need to jump to the Redis cluster list here. I have cleared all my clusters. You may still have your simple cluster running. Don't forget that clusters can cost money, so if you don't need it, please delete it or watch your AWS budget for charges. Okay, let's create a new cluster by clicking Create up here. This looks familiar, only this time instead of a cluster mode disabled cluster, we're going to enable it. Let's look at the values we want to set. I first chose cluster mode enabled here. This is going to give us the ability to add additional shards to our cluster. Remember, data is partitioned across shards, giving us greater scale, performance, and failover capabilities. Next, some of the basic info. I will call this cluster Complex Redis Cluster for clarity and give it a description. Replication and failover with multi-AZ. I'm choosing the latest Redis version based on our use case requirements. You may have a requirement for an older version. You can choose that in this field. I will leave the default Redis port as well as the default parameters. Remember, we are now able to add additional shards to our cluster, so I'll make sure we have 2 here. For node type, I'm going to choose the smallest version for our demo. You should see it pop up like this. You have a wide range of node types available. Choose the best option for your specific cache needs. Okay, let's look at some of these advanced settings. I want each of my shards to have 2 replicas, so I enter that here. And I will create a new subnet group for my cluster to live in. I'm calling it multi-AZ subnet group. And in the description, I say 2 AZ subnets, because down here I'm choosing our 10.0.2 and our 10.0.3 subnets. Remember, we built them in 2 different availability zones, hence our multi-AZ subnet group. This, of course, needs to be our new VPC first, so it will list our subnets below. Scroll down for some additional options. Down here we have the auto failover with multi-AZ settings. With the box checked, we have the option to do a couple of things. First, if you want to set up shards in a specific distribution of data, you can edit that here. For our case, the default of equal is perfect. What we do want to modify is specifying our own availability zones. If we left the default of no preference, in all likelihood, AWS probably would have made similar choices, but we're going to do it ourselves so we can see the values before the cluster is created. Here it shows our 2 cluster shards we chose to create. It also gives us columns for each node in our shard with a drop-down for each one so we can choose an availability zone to place that node in. These first 4 we'll leave in US East 1A, but scroll over to the last replica node and modify each of those to be US East 1B. Now we have our primary node and our first replica node in both shards living in East 1A, and each shard has a secondary replica node living in East 1B. This provides us some assurance that if an AWS zone fails, our data will still live in another zone and can be promoted to our primary, providing a level of safety across our cluster. I call that pretty resilient. Okay, enough on the multi-AZ. Let's look at security. Click the edit icon so we can put our cluster in the correct security group. We named our security group something easy to remember, so choose our Complex Redis Cluster S group. And now click Save. The rest should look familiar based on our previous module. If you want to see the cache, you would enter the path into this field. This go around, we're just going to create a new empty cluster. Scroll down a little more. You can choose to enable automatic backups here. We'll be touching on this in more detail in a future module. And finally, if you have a specific time of day you want AWS to perform maintenance, you can add that here. Otherwise, just choose the no preference option and AWS will decide the most appropriate time to run those changes. Now click Create. You should see our new cluster being created in our Redis cluster list, similar to this. Congrats on creating your first advanced cluster. It'll take a few minutes to get fully started, so let's end here. In our next section, we will finalize our network setup, our production EC2 server, and gain access to our cluster. See you then. Welcome back to the last part of our demo for setting up and connecting to a complex Redis cluster. This last phase is a bit more involved. Be prepared to use the AWS console, as well as a terminal window if you're on the Mac, or some SSH tool like PuTTY if you're on a Windows PC. To finish our network setup, we need to add the correct rules to our security groups. The easiest way to get to our security groups is via the VPC console. So search for VPC and click the correct item in the list. From here, we can link directly to security groups in the left menu over here. Let's start with the production server security group. Click on it in the list so you can see the tabs below and select inbound rules. Then click edit rules here. From here, click add rule and select SSH from the first dropdown. Then in the source, enter 0000/0, which will allow anyone from the internet to access our security group via the SSH port. Again, this isn't normally recommended. It's always better to keep this reserved to a specific IP address from your company's network, for example. But for simplicity, we will open to everyone for now. Add a quick description saying I'm giving it SSH access, and now I can click Save Rules here. Success. Move on and click Close. Okay, now choose our complex cluster group from the list like this, then inbound rules here and edit rules here. This time we add a custom rule. Your value should look like this. The key points are the Redis port 6379 and our open access as the source. And this rule is to open the Redis port to access from other groups in our VPC. Click Save Rules. Okay, time to build our production server. Click Close and use the Services menu to search for our next service. We want to create a new EC2 server, so search for EC2 and click the item. This is our EC2 dashboard. Click into our running instances here to create a new one. I have a previous instance that is still being terminated. You may have some or none in your list. To create a new one, click Launch Instance here. We can choose the first one for our production server, which is the Amazon Linux 64-bit machine. I select that option by clicking here. For a production server, I might normally choose something with a little more power, but for our demo, I'll choose this default T2 micro instance. Click Next down here. Only 3 changes we need to make on this screen. We want our new VPC we created earlier. We also want this to be deployed into the correct subnet, which is our public subnet of 10.0.1, which you can see here. And finally, enable auto-assign IP, so we get a public IP assigned by AWS. Then click Next. The default storage settings is fine. Click Next. I add a tag called name and set the value to Redis prod server, so we can easily find this later. Click Next. I want to use the correct security we created, so choose to select an existing security group here and choose the appropriately named group of Complex Redis Prod Server here. You can see it is going to provide us SSH access. Click Review and Launch. Alright, this is just showing us a quick review and a security warning that we discussed in a previous module, so you can just click Launch. Don't forget, either choose an existing key pair you already have downloaded, or create a new pair and download it. Either way, you'll need that PEM file so we can SSH into our server in just a few more steps. Click Launch Instance. You should see a similar screen. Our instance is starting up. Click View Instances to take a look at our new instance in the list. Okay, well, our instance starts up. Let's go back to our cluster and get some connection information so we can access it from the new server once it's ready. Use the Services menu here. Search for ElastiCache, or maybe you can see it in the recent history list over here like me. Click the arrow to open the details about the cluster. Before we grab the data we need, let's review what we created. You can see we have a total of 6 nodes in the cluster here. We have 6 because we created 2 shards, which also shows correctly over here, and we added 2 replica nodes to each of those 2 shards. So 2 replica nodes plus 1 primary node equals 3 total nodes per shard, times 2 shards equals 6 nodes. We also have multi-AZ enabled, and our cluster is leveraging our multi-AZ subnet group we created. Everything looks as it should based on our configuration we set up. Now let's get this configuration endpoint up here and copy it down for use later. Okay, head back to our EC2 list via the Services menu. Our instance is ready to go. Click on it in the list to see its details. We want to grab this public IP address for the next part of the demo. Once you have that, head to your terminal window if you're using a Mac, or launch your SSH tool if you're on Windows. I'll demonstrate on a Mac. From the terminal window, we want to run SSH. The command should look similar to this. You want to replace the IP address here with your EC2 public IP, and replace this key pair file here with reference to your key pair file. You should have downloaded that earlier. Hit Enter. If this is the first time accessing the server, you should see this warning. Type yes and hit Enter. Okay, we're now remotely connected to our production server. From here, we should have access to our new Redis cluster. That is, if all of our security was set up correctly. Let's start by installing a Redis client to our server. The first step is to install a compiler like this. Type the same command and hit Enter. If you see this warning, type Y and enter again. Once that's complete, we need to download the Redis client from the internet. Use this command to start the download and hit Enter. Once downloaded, we need to extract the contents of the file. Use this command to extract the content. Hit Enter. Once that's complete, we should have a new directory called redis-stable. Change that directory by typing this command and hit Enter. Now we're in our new folder. So type make disk clean like this and hit Enter. Should finish like this. Now type make to to finish the install process. Hit enter. Okay, if you see something like this, it means our install was successful. Let's use the new software to connect to our cluster. Type the command as you see it, but replacing the endpoint URL with the one you copied from your cluster details earlier. Then hit enter. Okay, we're now connected to our cluster. Let's run a few tests. Type get A. We get a nil response. That means key A does not exist in our cluster yet. When we built our simple cluster, we seeded it with a data file, so key A was loaded into our cache. For this cluster, we chose not to seed it, so key A does not exist yet. Let's set key A now to this value, key A set from config endpoint, and hit enter. The response is okay. We have now set our value at key A. Notice the IP address changes in the console. Since we're using the main configuration endpoint to access our cluster, it's deciding which of our nodes to use to process the request. In this case, it's the one that ends in 2.101. Let's try some other tests. If we type get A, we see our value. We know the cache is working. Now let's add a new key and value. This time we do a set Z to key Z set from config endpoint. Hit enter. Again, you see the console changes to a different IP. This time it's 2.213 instead of 2.101. That means the cluster chose to insert that data using a different node. One final test is to get those values again from the new node. Type get Z and hit enter. It returns our value and sticks us to the same IP node. Now type get A and hit enter. You can see we were redirected to a different node in the cluster where our data lives. This is a basic way to understand data partitioning. The cluster is spreading data across both our shards, and leveraging the configuration endpoint will keep the client access easy. It's also possible to get an endpoint for each individual node if your needs call for it, and access nodes very specifically. Let's jump back to AWS to see where we can find those endpoint details. Back in our cluster list, click on the cluster name to jump into our list of shards. You can see our 2 shards in the list, and both registering 3 nodes each. Click on the shard name to get the node list for that shard. Okay, now we can see each individual node, as well as each endpoint for those nodes. If you needed to access one of these individual nodes as part of your requirements, this is where you can find that information. One last final detail. If you click on one or more of these nodes, you can access some basic metrics about your cluster. Let's select all 3 of these nodes. Here you can see some cluster metrics. And in this particular case, I'm looking at the current items chart, which tells me we have 2 items in the cluster, our A key and our Z key. And all 3 of these nodes have that data replicated appropriately. These metrics can be used to monitor your cluster and help measure performance and when to potentially scale your cluster up if you have some degradation, or maybe even scale it down if you have excess capacity and just want to save some money. We've reached the end of this demo. Hopefully you found it useful in your endeavors creating your own Redis cluster in the future. Let's make sure we covered everything from our use case. We used the latest Redis version, check. We enabled replication and failover across 2 different availability zones. Checked both of those. We had 2 shards, so our data was partitioned correctly. And finally, we connected to our production server and successfully connected to our new cluster, adding data and verifying that the data was successfully stored across our nodes. Thanks for watching. In the next module, we'll talk about scaling and backing up our Redis clusters. So I hope to see you there. Welcome to this module of connecting and deploying Amazon ElastiCache. My name is Tom Compagno, and I'm excited to show you some of the more advanced features of ElastiCache. In the last module, we built and connected to a complex Redis cluster. In this module, we will be exploring some of the advanced features to show off the scalability and resilience ElastiCache can provide your application. Let's take a look at what this module will cover. First, we'll review our use case. Seems like those developers always need something. Based on those requirements, we'll go through a simple backup process to understand some of the details. Next, from a backup, we'll show how you can recreate a cluster by restoring it. Then we'll switch from backups to understanding scaling. First by scaling a simple cluster, then by scaling a more complex cluster. Finally, we'll review a few other details related to Redis clusters to finalize the module. Your company, Globomantix, has a development team in need of a production-ready Redis cluster for their new application. Globomantix needs the ability to back up and restore a cluster, as well as the ability to scale in and out a Redis cluster with minimal downtime. Based on that need, let's get going with our first demo. It takes place in the AWS console, so head there now. In this demo, and within the AWS console, we'll show how to run a backup on an existing cluster, then create a new cluster and show how to enable automatic backups. From the console dashboard, let's search for ElastiCache. Type the first few letters, and choose from the drop-down list here. From the ElastiCache dashboard, let's take a look at our Redis clusters by clicking here. To run a backup, let's choose our simple cluster, clicking the checkbox here. Now the backup option appears available, and we can click the button here. You can create a backup off either the primary node or one of the replica nodes. AWS suggests backing up from the read replica. They recommend this because the resources required to run the backup process will not affect the primary node, providing your cluster less interruption while the backup is running. For our example, we'll run it off the primary node and give the name Simple Cluster Backup. Now click Create Backup. Back in our list of clusters, we can check our new backup by clicking Backups over here. This is our backups list, and you can see our new backup is being generated here. Click on our new backup in the list to see more details. The backup contains all the information as well as the data from the cluster it was created. While this is working, let's look at another way to do backups on a cluster. We just ran through an example of manually running a backup on our cluster. Let's look at how to make this automatic. Back in our Redis cluster list, let's click Create to start the process of building a new cluster. This page should look familiar. Let's add some information. We'll call it our Auto Backup Cluster, choose a T2 micro for simplicity, and set our replicas to 0. Down below in the backup area, we have the option to have AWS automatically create backups for our cluster. If enabled, we can provide a retention period in days. In this example, AWS will store the backup for 1 day. Increase this value to meet your specific needs. You can also let AWS choose when to run the backup like we have selected, or you can have a required maintenance window. You can force the backup to occur during that custom window of time. I'm not going to create a cluster in this case, but let's jump back to our cluster list to see how we can enable or disable automatic backups of an existing cluster. From our list, let's select our simple cluster again by clicking on the checkbox here. While this will show our cluster details, it also enables the Modify button up here, so let's click that to see what options we have available to us. There are a number of items we can change on this simple cluster. Some we'll talk about later. For now, I want to point out the ability to enable or disable automatic backups from here. This is a convenient way to update an existing cluster without starting from scratch. If you make changes here, remember you can choose to have them immediately start the process when you click Modify, or you can uncheck this option and let the changes occur during the next maintenance window. It's a good way to make a change during business hours, while actually have it modifying your cluster after hours. If we choose to enable automatic backups, I'm provided with similar options as the manual mixed with previous automatic options you get while creating a new cluster. I can choose my node, as well as my retention period. It also allows you to update the default backup window if you find it undesirable. That's it for backups. Next, we're going to take a look at scaling. Redis and ElastiCache provide a number of different options to scale your clusters. They're dependent on cluster type, and while some can be done live, others require downtime and possibly updates to your application because you'll essentially be building a new cluster. Let's start by looking at the ways to scale a simple cluster. By simple, I'm talking about a cluster with cluster mode disabled. First, you can remove nodes simply within the console. Your cluster will automatically rebuild and readjust to the loss of nodes. You will want to remove nodes if you have an excess read capacity and are looking for ways to reduce costs. Second, opposite to removing, you can add nodes if you find you need additional read capacity. This will be a similar process. If your cluster has significant more memory than is required by the cached data, you can downgrade your node type to also save money. This is not possible without recreating the cluster from a backup and choosing a smaller node size. Finally, if you find your cluster is maxing out on memory, you can easily modify your cluster and upgrade to a larger node type within the console, making a very convenient way to increase your cluster's capacity. Let's take a look at some of these options in more detail. Okay, from the AWS console, we will restore a cluster backup and show how to reduce the node size. Next, we'll modify an existing cluster and add read capacity by adding replica nodes. Finally, we'll increase the overall memory capacity in a cluster by upgrading the node type to a larger size. Let's get started in the console. Let's begin from our Redis cluster list. You can see our existing simple cluster here and its node type, which is T2 small. Let's reduce that type to a T2 micro. Click on backups here. Here you can see our backup of the simple cluster we made in a previous video. Click on the checkbox here to view the details. Okay, from here we can now access the restore button up here. Click that. This is our restore form. Pretty straightforward. Let's adjust some details. First, give it a new ID. We'll call it simple cluster smaller. Then down here, we change from a T2 small to a T2 micro, which will create the cluster with a reduced node type. The rest will leave the same, and click continue. Our backup list indicates the backup is being restored into a new cluster. Let's jump to the cluster list and see what it shows. Click Redis over here. Here's our list. You can see our new simple cluster smaller cluster being created with a node type of T2 micro. Once complete, it'll be a copy of our previous backup we made from our simple cluster. Next, we will increase the read capacity of our cluster by adding nodes. Let's jump there. You may find your cluster's memory is working out just fine, but access to that cluster has increased higher than it can process. You notice most of your traffic is simply reading from your cluster. There's a simple solution in this case. You can add a read replica to your cluster as long as you've not reached the 5 maximum for a basic cluster. Let's take a look. Starting in our Redis cluster list, let's click on the name field of our simple cluster here. This takes us to the node list for our cluster. Here you can see we have 2 nodes, a primary and 1 read replica node. To add additional nodes, simply click Add Nodes here. A simple pop-up form will appear asking for some basic information about our new node. I leave the cluster field to the default and include a name of added node for clarity. Then I decided to add this node to a specific availability zone. Here I chose US East 1A. Now click Add. It may take a few seconds before a new node shows up in the list. Hit refresh here a few times or exit the screen and return in a few minutes. Our node is being created. Adding read capacity is as easy as a few clicks in the console. Now our cluster will continue to provide data at appropriate speeds to the requesting applications. The final simple cluster scaling technique we will discuss is upgrading the node type. Unlike downgrading, it's a much simpler process. Let's take a look at that process next. Upgrading a node type for Redis is essentially increasing the overall memory capacity for the cluster. Use this method if you find your cache is maxing out its memory. To start, let's use our downgraded simple cluster smaller cluster and upgrade the type back to a T2 small. Select it from the list. From here, we can now modify the cluster by clicking Modify here. This is the form we also saw during our backup demo. This time we'll select a new node type from the node type field here. We selected cache T2 small, which increases our overall memory on our 3 nodes from 0.5 gig to 1.5 gig, or a total of 4.5 versus the previous of 1.5 gig. We get some warnings here telling us that our cluster will be temporarily unavailable while the changes are made. But compared to the restore process we had to follow to downgrade our node type, this is a much more seamless workflow. Click Modify here. While our changes are being applied, it'll show the status as modifying in our cluster list. Just another simple method of scaling a cluster. Let's move on in the next series of videos to how to approach scaling on a more complex cluster. Scaling a complex cluster is similar in some ways to a standard cluster, but offers some additional online options as well. Let's take a look at what we have available. First, upgrading node types on a complex cluster is not available online like it was for the simple cluster. Downgrading a node type is the same. If you want to change your node types in any way on a Redis cluster that has cluster mode enabled, you must do a backup and restore process to create a brand new cluster with the new node type selected. While a bit more involved, it is still a fairly simple process as we've already demonstrated. Next, and what we will be demonstrating, is how to add shards and additional nodes to our complex cluster. It is an easy process and as easy to remove those shards and nodes as well. By adding shards, you are increasing all capacity as each shard includes a new primary node helping to spread traffic across yet another node. Adding nodes increases read capacity only, as you'll be adding read replicas just like on our simple cluster example. The demo is simple. We'll start in the console. First, we'll walk through adding a new shard to our cluster, then see the process for adding nodes to a shard. From our cluster list, select the complex cluster here. Here you can see our current cluster structure. We have 9 total nodes. Those nodes are spread equally across 3 shards. Let's start by adding one new shard to the cluster. Click on the cluster name to view more details. From here you can see our 3 shards. This is our key list where we will add shards and nodes. While we won't be demonstrating the process, notice this is also where you would delete shards as well as delete any replicas. For our next step, click Add Shards here. The pop-up explains that adding shards provides a larger cluster to spread data across, which it will do once the shard is running, and that process could take some time. All we want to do is add one additional shard to our cluster. So we enter a 1 in this field to represent the additional number of shards we want to add. Then click Add. Back in our shard list, you can see our previous 3 shards and our new shard being created. The cluster is processing and spreading out its existing cache data across all the shards, including the new one. This gives our cluster increased capacity, and if we added additional availability zones, would have improved our overall failover abilities as well. Back in the main cluster list, you can see our complex cluster still working, but now showing we have 4 total shards and a total of 12 nodes, 3 for each of those shards. Give it time to finish processing and check back in a few minutes. Once complete, if you review the details of the shard in our complex cluster, you should see this new list of 4 shards. Notice the slots are redistributed, meaning our data has been spread across all 4 of our shards now. In the next step, we'll follow a similar process and simply add a node to a specific shard. Similar to a simple cluster, if you need to increase your complex cluster read capacity, you can do that by adding additional read replicas. In this demo, we'll show how to add one new replica node to one of our shards. Jumping to the complex cluster shard list, select a shard in the list by clicking here. This shows us options at the top. Again, here we could delete the shard or delete replicas from a shard, but in this case, let's add a new replica node to this one shard. Click Add Replicas. The pop-up tells us what we get by adding a replica. It states that it will provide increased read scalability, which sounds great, so let's fill out the form. Instead of telling it how many new replicas to add, we need to tell it the new total number of replicas we want in the shard. Previously, we had 2 replicas as well as our primary node for a total of 3. Let's increase the total to 4 nodes by updating the new number of replicas from 2 to 3 here. As with all node configurations, you will have the option to choose which availability zone your new node can live. Either leave it up to AWS or create your own strategy based on the client's needs. Click Add. You should see our shards being modified to accept the new node. Wait a few minutes and refresh the list. Once complete, you should see the additional node in the cluster you chose. In our case, our 0001 shard now has 4 total nodes, 1 primary and 3 replica nodes. Congratulations on a successful cluster scaling. Let's review what we accomplished in this module. First, we successfully backed up a cluster manually. This process is useful for taking snapshots to use as restore points for changing aspects of a cluster, or even as a way to seed clusters as we've seen in previous modules. We also reviewed what automatic backups of a Redis cluster entails, and some of those options as well. We learned how to change node types, increasing and decreasing memory capacity, of our overall cluster. We looked at how to add nodes to increase our read capacity, as well as adding full shards into a complex cluster, which improves overall cluster capacity across many dimensions. I've tried to present a number of ways to modify Redis capabilities, but ultimately what you'll end up needing will depend on your cluster's specific performance metrics. Be pragmatic at keeping your cache at just the right size to avoid wasting money, but also providing the best service to its clients. Welcome to this last module of connecting and deploying Amazon ElastiCache. My name is Tom Compagno, and I'm excited to show you some of the more advanced features of ElastiCache. In the previous module, we explored some of the advanced features to show off the scalability and resilience ElastiCache can provide your application. This module, we're going to show you another type of cluster option called memcached, or also pronounced memcached. Let's dive into our final topic, which is how to build and scale a memcached cluster. We will start, as always, with a use case to help us understand the options we have available to us and how they apply to a real-world scenario. We will explore memcached immediately by jumping in and creating a cluster that meets the expectations of that use case. Then we will look at how to potentially scale that cluster by adding additional nodes. And finally, we will review different ways to access our cluster, similar to the previous Redis modules, as well as dig into how memcached differs from Redis. Your company, Globomantix, has a development team in need of a production-ready memcached cluster for their new application. Globomantix has decided to store their e-commerce users' most recent purchases in a cache for faster access, and to take some of the load off their transactional databases. They need to create a cluster and have the ability to manage the nodes and plan it to scale as needed. Based on the volume of data, they estimate a cluster with the smallest node type and 3 nodes will provide the power they need to support the application. It will only store basic data, which will be string-based product IDs. They want the caching platform to be multi-threaded in case they decide to upgrade node types and scale the cluster vertically as the application grows. There is no need to back up this cache, as recent purchase data can be reloaded from the transaction database very quickly. Let's take a look at our first demo. It will start in the AWS console, so head there now. This will be a quick demo from the AWS console. We will want to walk through the fields for creating a memcached cluster. Many of them overlap with the Redis options, so if you have watched the previous modules, some of this should feel familiar. Back in our ElastiCache dashboard, instead of starting with Redis today, let's jump to the memcached area by clicking here. This is a very similar list view as the Redis cluster list. And similarly, click Create to get the process started. The form literally is exactly the same as the Redis Create form, but let's switch it to the memcached view by choosing this option. Still, many of the same fields. Let's start with the node type here. The options for the type of node are similar to Redis. For our scenario, the T2 micro option satisfies our need. Multiply 0.5 gig of RAM times the 3 nodes we plan to add to the cluster, and it gives us roughly 1.5 gig of cluster capacity, minus some overhead. Click Save. Let's name our cluster something simple like memcached cluster. We will choose the latest engine version for our example. but this field is where you can launch a cluster on older versions if your requirements demand a specific older version of Memcached engine. Remember, the port 11211 is the standard Memcache port, and we'll talk about it in a later video when discussing how to access this cluster. We don't have any special parameter needs, but just like Redis, if you have multiple clusters with the same parameter needs, they can be grouped to avoid setting specific parameters on every cluster in your list. And as per the requirements, we want to choose a total of 3 nodes to sit in this cluster. Memcache nodes are different from Redis. Let's take a look at a diagram. A Memcache cluster can be visualized this way. A cluster has 1 to 20 nodes total. Each node can live in its own availability zone, and data is partitioned across all the nodes. Data is not replicated across nodes, meaning each node does not have the ability to store all cluster data. So if a node fails, some data will be lost. The more nodes and the more availability zones within a cluster means less data will be lost to a single node or availability zone failure. Okay, back to our settings for creating the cluster. If you have gone through our previous Redis modules, you should have our network already set up. Select our multi-AZ subnet group we created, which contains our 2 private subnets and 2 different availability zones. Then choose the complex Redis cluster security group here. We will let AWS do maintenance whenever they want, and we don't need notifications. Click Create here. Back in our list, you can see our cluster is under construction. Give that a little time to finish, and then move on. Once complete, open the details of our new cluster by clicking this arrow. From this view, we can see things like the general configuration endpoint. Copy this if you want to access the cluster in the future. It provides a single point of entry to each cluster node endpoint. Since we have 3 nodes, let's look at those. Click on the cluster name here. You should see a list with 3 nodes for our cluster. If you plan to access each node independently, you can copy the individual endpoints from this location. We have successfully created a Memcache cluster with 3 nodes. Next, we'll look at a way to scale our cluster. In the next demo, we will again start from the AWS console, so head there now. Our primary goal during this sequence is to add an additional node to our existing Memcache cluster. It is a straightforward process which makes Memcached a pretty versatile caching technology. After we add our node, we will go back through and look at what kind of updates we need to make to our security group to allow access to our new cluster. From our Memcache cluster list, let's click on the name to jump into the node list here. From our node list, to add a new node, it's as simple as clicking Add Node here. As I mentioned previously, the more nodes and the more unique availability zones you have in your cluster, the more resilient your cluster is to failure and data loss from those failures. So from here, you can choose the number of additional nodes. Remember, a cluster maxes out at 20 nodes. Then, choose how we want those nodes spread across whatever availability zones you have set up in your network. For this demo, let's just add 1 new node to see what the process looks like, and I'll let it choose the best AZ for that node. If you are making updates to clusters, you will often see this Apply Immediately option. It is self-explanatory in that if you choose yes, it'll start processing the change right away. If you choose no, then it will do it during the next scheduled maintenance window. This allows you some scheduling functionality and allows you to make changes during windows of your choice. Click Add. Back to our list, it may take a few seconds to show up, but you can see our additional node is being created now. Once complete, you should see it as available and can also check which AZ AWS decided to deploy it. Our nodes are spread equally across zones. With the previous module, we created a custom VPC in AWS and set it up in such a way that a production server living in one security group and subnet could access our Redis cluster. Let's take a look at how we can tweak that configuration to allow the same server to also communicate with our Memcache cluster. Let's jump to the VPC area in the console by typing VPC into the services menu search like this. From the VPC dashboard, let's jump to our security groups here. The group we need to tweak to allow similar access to Memcached is the complex Redis cluster S group here. Click the checkbox. In the details below, you can see our existing Redis rule here. This was set to port 6379, and we opened it to anyone that can see this group. Let's add a similar rule for Memcache by clicking Edit Rules. You will want to add a new rule and enter these values. Notice everything is the same except we use the Memcache default port of 11 to 11. and add a slightly different description. Once complete, we save the rules by clicking here. Our security group now opens itself to Memcache traffic as well. You can see the new rule here. Remember, our AWS only access network diagram from the previous module on Redis looks something like this. So what we just finished doing was adding port 11 to 11, as seen here in the diagram, to our security group that holds our EC2 server. In reality, our diagram would look a little different, as it would also include our Redis port and our Redis cluster living in the same security group and subnets as our new Memcache cluster. But I'm simply showing the general network configuration, which allows other AWS systems to access a Memcache cluster. If you want to access your Memcache cluster from outside of AWS, you can leverage work from the previous module as well. We won't be demonstrating how to modify this version of the VPC, but remember, we created this version to allow outside AWS access into our cluster. We did that by translating all our cluster requests through a NAT, Network Address Translation EC2 server. If you would like to do the same for Memcache, review the Redis module where we applied this configuration, but anywhere we use the port 6379, use the standard Memcache instead, which is the 11 to 11 port. Enough with networking. Let's do a quick connection test, and then take a look at some differences between Redis and Memcache to finish up this module. In order to follow the next steps, it is assumed you have your networking components and EC2 instance still set up from the previous modules. If not, go back and follow those steps and head back here when you're done. From my Mac terminal window, and like the previous modules, I'm going to SSH into the server that I put into our server security group, which has the SSH port open. Your command should look similar, but remember, swap out the IP and the key file for your own. This is our normal first sign-on warning. I type yes and hit enter. Once connected to my server, I'm going to show the simplest way to connect via the command line to a Memcache cluster, which is via Telnet. But I need to install the Telnet client first. I type this command, sudo yum install telnet, to kick off the install. If you see this warning, just type Y and hit enter. Okay, now that Telnet is installed, let's connect to our Memcache cluster using the configuration endpoint we grabbed in the earlier step. If you don't have it, just go look at the details of your cluster in the AWS console and you can find it there. The connection command is simple. Telnet, then the host name, and then our Memcache port. Hit enter. It tells me I'm connected. Let's run some quick tests. First I type get A and get no data back, which is expected. Our cluster should be empty. Let's add some data to the A key. Start by using this command. Set A 0, 100, 9. The 100 is an expiry value, and 9 is the number of bytes my value will be. I haven't actually specified a value yet, so hit enter. Okay, now I type memcache as my value, and I hit enter again. It tells me my key value pair is stored. Let's double check the values there by typing get A. It correctly returns my new value here. We have successfully connected to our Memcache cluster. Some of the key differences between the two caching technologies are listed here. First, Memcache is not capable of converting to a permanent store. You cannot back up a Memcache cluster like you can with Redis. Next, with Memcache, you can only store basic data types like strings or simple objects. Redis has a number of more complex data types available, like sorted sets and the ability to use the cluster as a publish and subscribe system. Memcache is multi-threaded, so it can make better use of multiple cores within a single node. Redis is single-threaded, so understanding the requirements related to cluster usage and traffic are important when choosing a technology. And finally, Memcache does not support encryption. If that's a requirement, then you must leverage Redis to meet that need. A couple other things to note about Memcache. Unlike Redis, it does not provide high availability. There will always be some data loss on a node failure, but as I mentioned before, the more nodes in your cluster, the less data that will be lost because of data partitioning. Failover has the same result. It can be mitigated by adding your nodes to as many availability zones as possible. The more nodes and the more zones, the less data loss from a node or full zone failure. Memcache has a large community, and most popular programming languages have a Memcache client available. This is a list of a few for Ruby, PHP, and Python. but you should be able to find a client for your specific coding needs without any issue. So what did we learn? We learned how to create a new Memcache cluster. The process is very similar to building a Redis cluster, and even easier to get up and running. While Memcache doesn't have nearly as many scaling options as Redis, adding more nodes is as easy as a couple of clicks in the console. If you want to change the node type in Memcache cluster, you need to actually just create a new cluster with the new node size, and then update your application to point to the new cluster endpoints. There's no quick way to vertically scale an existing cluster. Finally, by leveraging our previous network and from our Redis build, we learned a few small tweaks to the same network provides the access we need to include our Memcache cluster into our application's infrastructure.